We're going to talk about what are called Taylor polynomials. Of course, having a name on them like that, they're named after somebody, and the guy's name was Brooke Taylor. So he's the one that's famous for Taylor polynomials. Taylor polynomials are ways to find polynomials, which are like additions of x squareds and x cubes and that sort of thing, and subtractions, to represent other functions like sine, cosine, 1 over x, all that kind of stuff. So there are some pieces to Taylor polynomials. First of all, you've got to decide how big your polynomial needs to be. Do you want a quadratic? Do you want a cubic? What do you want? The other thing is you've got to figure out where you want it centered. What is the most important point in a sense? So we're going to try to do that. All right? So here's the pattern for Taylor polynomials. F of x, the function, whatever it is approximately equal to, and then we start putting f of c, that's c stands for center, plus f prime at c times x minus c over 1 factorial. Now notice I've got no derivative. I've got a first derivative, a first power, and a 1 factorial. Then we've got f double prime of c x minus c squared 2 factorial. Now you can probably see the pattern. Double prime, second power, 2 factorial. So it just continues with that pattern. So that's what Taylor polynomials look like. Now let's use an example. I'm going to choose the example of ln x. So let's say that f of x is equal to ln x. So if we need to find a second degree, so find a second degree or quadratic style, so second degree Taylor polynomial, we're going to have to go through here and find the first derivative and then find the second derivative. Now let's center this. So let's say it's centered at 1. Now you can center it anywhere you want as long as the natural log of x is defined. So here's what we're going to do. We are going to take the derivative of ln x. So we've got f of x is ln x. Before I take the derivative, let me find f of 1. That's ln 1. ln 1 is 0, as you might recall. Then we've got to take f prime of x. That is 1 over x. F prime at 1 is 1 over 1, which is 1. Then let's take f double prime of x, and this is equivalent to x to the minus 1, so this is minus 1x to the minus 2, or minus 1 over x squared. So f double prime of 1 is minus 1 over 1 squared, which is minus 1. So now I've got two derivatives, and I'm all set to make my second degree Taylor polynomial centered at 1. So the way that we do this is we say that f of x, or ln x in this case, is approximately, because this is not exact, but it's close, f of c. F of 1 is 0, plus f prime of c. F prime of 1 is 1 times x minus 1 to the first over 1 factorial. Then for the next term, we take f double prime at 1, which we got as negative 1. We've got x minus 1 squared over 2 factorial. Now you could keep going, and if you went forever and ever and ever, then you would have exactly the natural log of x. That is one of the things that is so cool about this. We're turning a logarithm into a polynomial. A transcendental function into an algebraic function. Well, let's simplify this just a little bit so you see the algebra involved. 0, I could get rid of that, so let me do that. Here I've got 1 times x minus 1 to the first over 1 factorial. Well, 1 factorial is 1, so this is x minus 1. Then this one is minus, so I'm going to put minus, and I've actually got 2 factorial down here, so that's 2 times 1, so that's 1/2, okay? Then I'm going to square this out, so I've got x squared minus 2x plus 1. So if we try to put things together, we've got this. We've got ln x is approximately x minus 1 minus 1/2 x squared, and then multiplying here we've got plus x, and then we've got minus 1/2, or minus 1/2 x squared. We've got x plus x, so we've got plus 2x, minus 1 minus 1/2, so minus 3/2. What you might want to do is you might want to attempt to graph that on a graphing calculator or website or whatever, and you might want to graph natural log of x with it. And you'll notice that very, very close to the value 1, which is the center of this thing, these are virtually the same. They are not identical, but they are very close. So it is an approximation.